Welcome to Cookie's Maths and Science Hub. Today we'll be looking at the concept of energy, what it is, its different types, and how it is conserved throughout closed systems. So, what is energy? Energy is the ability or capacity of a system to do work or cause a change. It enables objects and systems to perform tasks, move, or produce changes in their surroundings. Most common examples of energy is if you're running, you've got energy as you're moving, or if something's falling, it has energy as it's falling. However, there are many different types of energy, which we'll discuss shortly. All energy is measured in the units known as joules. This is named in honor of James Joule, who contributed a lot to energy research in the early days of science in this field. As mentioned, there are many different types of energy. I've listed some on the right here, such as kinetic, potential, thermal, chemical, nuclear, electrical, sound, and elastic. It's important to realize that energy can change from one form to another through various processes, such as conversion, transfer, and transformation. These are really core ideas when looking at the conservation of energy. Some of the main forms of energy that we're going to look at are kinetic energy, which is associated with motion or moving of objects, potential energy, which is related to position or state. Thermal energy and chemical energy are two more popular ones. We're not going to discuss them too much in this video, but thermal energy obviously being associated with temperature, and chemical energy looking at the bonds within atoms and molecules and stuff like that. The most important idea when dealing with energy is the law of conservation of energy. This states that energy cannot be created or destroyed. It can only change from one form to another or transfer between objects. This means whatever energy you're putting into a system will come out of that system. Now, it doesn't necessarily mean it'll be the same energy, same type of energy as it might transfer or transform, but it's still the same amount of energy. So you can see on the right here, our energy in equals two different energies coming out, but those arrows equal the same length. In a closed system, any closed system, the total energy remains constant, which illustrates this principle really well. In open systems, it's a little harder to track as you can lose energy to a lot of different things. I like to think about it. If you drop a ball, you'll notice it doesn't bounce back up to the same height. Well, that's because of air friction, so energy lost to heat. Sound, as you know, the ball makes a noise when it hits the ground, and a lot of other factors as well. We're going to focus more on these closed systems as it allows us to do a lot more with the calculations and different factors within conservation of energy. Before we get into more complex calculations, let's look at two core types of energy: gravitational potential energy and kinetic energy. We'll start with potential energy. So potential energy is energy stored due to an object's position or state. Types of potential energy include gravitational potential and elastic potential. Gravitational potential energy is the one we're going to focus on today. This is the energy an object possesses due to its height above the ground, and it relates directly to the force of gravity on an object. In a calculation sense, gravitational potential energy is equal to the mass of an object multiplied by gravity, which is 9.81 meters per second squared down, multiplied by its height. By completing this calculation, we can solve for what the gravitational potential energy of any object is if we know its mass and its height, assuming it's on Earth and we know its gravity as well. So gravitational potential energy, or GPE, is equal to mgh, mass times gravity times height. Let's look at an example now. Over here I have a ball of mass 1 kilo and it's sitting on a table that's 1 meter above the ground. So we know gravitational potential energy is equal to mass times our gravity times our height. So if I place those numbers in, we have a mass of 1 kilogram. We multiply that by our gravity, 9.81, and we multiply that by our height, which in this case is 1 meter. So in this case, it's just 1 times 9.81 times 1. So it's just going to be 9.81, remembering our units, joules. Remembering all energy is in joules, so we need to make sure we include that when we write out our answers for these problems. Kinetic energy, on the other hand, is the energy associated with the motion of an object, and is one we see every day, and probably the one people are most familiar with when we think about energy and think about that it is objects moving. It depends on the object's mass once more, as well as its velocity or its speed. Those two things are different, and I recommend checking out our speed versus velocity video for more information on that. However, we will refer to them back and forth within this video today, as they are quite similar in properties. So looking at an equation, Our kinetic energy, or Ke, is equal to half times our mass times our velocity squared, or Ke equals half mv squared. Let's look at a basic example now. We have our runner here of 80 kilos, and they are running at 6 meters per second along this track. So our Ke is equal to half times mass times velocity squared is equal to half times 80 times 6 squared is equal to 40 times 36. Just going through the steps of the equation there, half times 80 is 40, 6 squared is 36. So 40 times 36 equals 1,440 joules. Once again, remembering it's important to use those units. Whilst what we've explored so far is that grade 7 to 10 level, the remainder of the video is in year 10 plus content. So I would consider clicking off the video now if that's all you need, being sure to like, share and subscribe, and check our channel out for other videos at your level. Or if you'd like to try and extend yourself, watch on. But as I said, the rest is a little bit more complicated and goes into more of the mathematics involved with this side of physics. Mechanical energy is the combination of potential and kinetic energy. When an object is moving and it has gravitational potential energy, we say it has mechanical energy. Writing that out as a formula, we could say mechanical energy is equal to gravitational potential energy plus kinetic energy. Let's look at an example now. Our runner has continued his run and is now running up a hill. Same mass, 80 kilograms, at a speed of 4.0472 meters per second. I know that number's a bit tricky, but I'll explain why shortly. And a height of 1 meter. So we know our mechanical energy is equal to our gravitational potential plus our kinetic energy. So plugging in our numbers into our two equations, remembering gravitational potential energy is mgh, so 80 times 9.81 times 1, mass times gravity times our height, equals 784.8 joules. Our kinetic energy, on the other hand, equals half times 80, which is our mass, times 4.0472 squared, being our velocity in this case, which is 655.2 joules. Finally, remember we need to add them together for our mechanical energy. So our mechanical energy is going to equal 1,440 joules. This is where that core idea of energy conservation and the law of conservation of energy comes into place. If we look at our runner when he was on that flat, we had just kinetic energy and it equaled 1,440 joules. If we look at our runner up the hill, he has mechanical energy, but he still has that 1,440 joules. Initial energy will always equal final energy in these kind of problems. Yes, energy can be lost in the system, such as through friction or heat, and other sounds and other such effects, but that will be mentioned in the question and have to be included in your calculations. In this case, we can assume it's a frictionless system, as that energy has fully transferred from kinetic energy into mechanical energy. Obviously, some of it's still kinetic energy, but some of it is now gravitational potential energy. That's why the number was a bit weird for velocity, as I had to pick the numbers and I had to make it work for this equation. So I could show you that the kinetic energy is equal to mechanical energy in this frictionless system. Let's use this core idea of initial energy always equals final energy to do some more complex problems and solve for some unknowns. Okay, we're going to look at a cart going down a hill. This is a common problem you'll see when looking at these kind of examples and conservation of energy problems. So we know the speed of the cart at the start is 16 meters per second. We know it weighs 180 kilos and we know it's 24 meters up. Let's look at what our question is asking. What is the speed of the cart when it reaches point A? And we're assuming no friction in this system. So we know our initial energy is going to equal our final energy because that's the conservation idea. That's always the same. So our initial energy, in this case, we're going to have gravitational potential and kinetic initially so we're going to have mechanical energy because it's at a height and it is moving to start with. Now our final energy, or our energy at point A on our diagram, it's on a flat surface, it's not elevated, so it's only going to have kinetic energy. So our final energy is going to equal our kinetic energy at point A. You'll see in my calculations, I've got a little I next to it. That's to indicate initial energy, and F is to equal final energy. So I have kinetic energy initial when it's at the top of the hill, and kinetic energy final when it's at the bottom of the hill. So calculating our initial energy, we have mgh for gravitational potential. So we have 180, that's our mass, times 9.81, our gravity, times 24. which is our height in this case, plus our kinetic, so half times 180 being our mass, times 16 being our velocity in this case, squared. Don't forget the squared. Often comes up that people will forget to put the little squared in, and obviously that'll make your numbers wrong. Almost forgot to say it then myself. Plugging all that into a calculator or doing it step by step, granted, when you start to get into these more complex problems, I would say you would always be allowed a calculator and you'd be silly not to make use of one. That equals 63,653.4 joules. Now, remembering that core idea, our initial energy always equals our final energy. So we know that number, that 63,653.4, is going to equal our final energy, which is our final kinetic energy. So we can have 63,653.4 equals our kinetic energy final, which is equal to half times our mass times our unknown velocity squared, because we're trying to find that velocity. Half times 180 is going to give us 90. So then we'll have 63,653.4 equals 90 v squared. So then our v squared is going to equal that 63,653.4 over 90. Remembering to get rid of a multiplication, we divide it on both sides, which is then going to give us 707.26. Now to get the v by itself, the opposite of squaring is to take the square root. So we have v is equal to the square root of that 707.26. So our final speed or final velocity is going to be 26.594 meters per second. Okay, let's look at another example now. Similar one, similar setup, but with some slightly different numbers and a slight change to the problem. So same thing again, cart's coming down the hill. We're going to try and find its speed when it reaches point A. In this case, it has a starting speed of 11 meters per second. We have a slightly heavier cart, 200 kilograms, and it's at a slightly different height of 21 meters. The question is asking, what is the speed of the cart when it reaches point A? And we're told to assume that 4,000 joules of energy is lost to friction. Okay, let's go through the steps once again. We know our initial energy equals our final energy. We know our initial energy equals our gravitational potential energy plus our kinetic energy. And our final energy is equal to our kinetic energy at that point A. There's no gravitational potential because it's on a flat, plus that 4,000 joules. Because we know that 4,000 joules has been lost to the system, but you've got to remember, it hasn't actually been lost. It's still there. It's just been transferred or transformed into that heat energy. So our final energy has to include that in our calculation. Okay, let's calculate our initial energy first. Our mass is 200. Our height is 21 meters. So 200 times 9.81 times 21 gives us our gravitational potential. For our velocity, it's 11 meters per second at that starting point. So our kinetic is going to be half times 200 times our mass times 11 squared. Remembering again, be careful with the squared. Plugging all that into your calculator, you get 53,302 joules. Therefore, that 53,302, knowing our initial equals our final, is going to be equal to our kinetic plus that 4,000 joules we've lost to friction. So 53,302 equals our kinetic plus 4,000, which is equal to half times 200 times v squared plus that 4,000. Moving down into the next line, I've taken that 4,000 from both sides. So we've left with 100 v squared on the right-hand side because I've multiplied half by 200. And on the left-hand side, we have 53,302, take 4,000. Our next line down gives us v squared because we then divided both sides by 100. So v squared equals 49,301 divided by 100. So our v is going to be equal to the square root of that answer, which is 493.02. So once we've taken away the squared, remembering square root both sides, we'll get rid of a squared symbol or value. So v is equal to the square root of 493.02, giving us our final velocity of 22.204 meters per second. Thanks for watching. Hopefully now you have a sound understanding of energy and its concepts and how to use it in some more complex calculations if you watch that part of the video. Be sure to like, share and subscribe this video and look around our channel for any other videos that are helpful in your maths, science studies. Hope to see you again soon.